Okay, gentlemen, so hopefully your exam went, okay. Like I said, I'm probably going to grade about 50 out of 80 points on just completion, and 30 points I'll pick some problems and actually grade them. So this shouldn't kill anyone's grade, plus you had all the resources you could want to use it, so it should be okay. So we're going to continue and move on to the next section, which is gases and gas laws. So I'm going to introduce that today. You're going to get a worksheet, and all of that stuff is outlined in the Power School page. So you'll be able to check it all out there, and I'll have uploaded, in addition to this video, the smartboard notes that you're going to see and the PowerPoints that I'm going to go through, and that's all linked there. So gas laws is next, and that's what we'll be doing. So good luck. Okay, so today we're talking about gas laws. And first of all, one thing to note, all gases have the same physical properties. It doesn't matter what their chemical identity is, how different they are, they will act very different chemically. Again, you breathe in oxygen gas, pretty good. Breathe in chlorine gas, you're having a less good day. That's a chemical reaction. But physically, they act the same way, regardless of whether it's something tiny, like hydrogen gas that's only 2 grams per mole, or something like sulfur hexafluoride, which is a very heavy gas at 146 grams per mole. They both act the same. And the reason they act the same is because of how gases are. Solids and liquids are really, really compressed. So the compressed or condensed states of matter, their particles are right on top of each other. So how big their particles or small their particles are matter a lot more because, again, when you're compressed, it affects how much space you take up. Also, things like intermolecular forces have way more effect on them because they're much closer together. And intermolecular forces have stronger attractions and repulsions when you're closer together. Gas particles are so far apart and moving so quickly that intermolecular forces are pretty much negligible. They barely affect them, if at all. In fact, for most of what we're doing, we're going to assume there's no intermolecular forces affecting them at all. So here you can see my awesome not-to-scale rendering. I'm waiting for my art award of hydrogen gas, H2, and SF6. There are actually 6 little yellow dots around the sulfur, so I should get some credit for that. As you can see, though, if you spread them out enough, and they're mostly empty space, it really doesn't matter how big they are. They're still about the same distance from one another. And since they're about the same distance from one another, and they're going to be moving, we'll find out, with the same amount of kinetic energy at the same temperature, they have the same physical properties. So I'm going to come back to what we mean exactly by physical properties. But first I want to introduce gases a little bit. So I'm going to go over a few slides of the PowerPoint. So it'll be just like being in class. And then we'll come back to my board notes. So one thing of note, gases have been around, been studied for about 300 years. People have known about them for about 300 years. People knew of air. They didn't really understand what it was. But the first gas to be studied was air, once they figured out that it was like a state of matter and that's what was going on. And when it was initially studied, they thought it was a pure element. You get a sample of air and try to separate it out or determine that it's not just one thing. It's fairly impressive that we were able to do it even, in the 1700s when they figured that out. That's some impressive, science work there. So air was studied, and then they figured out, oh no, air is a mixture. It's not a single thing. And they thought they'd have to scrap all their data. Scientists were like, oh, now we got to look at each gas individually. And it turned out not so much, because the physical properties of gas, of all gases, are the same regardless of their chemical identity, which means if you have a mixture, the particles are going to act the same whether it's carbon dioxide or nitrogen or oxygen. So the work that had been done up till then did not have to be abandoned. It turned out it was fine. So again, gases have these same physical behaviors. And I'm going to talk briefly about what those physical behaviors are. But first, I want to talk about something called the kinetic molecular theory. I think I mentioned this once or twice before when we were talking about intermolecular forces, but the kinetic molecular theory basically explains a lot about how particles work and how they interact with one another. So it explains things like states of matter and such, but we're interested in it with regards to gases. So kinetic means motion, so kinesiology is a study of human motion particularly, and molecular refers to molecules. So the kinetic molecular theory means the motion of molecules theory. So this just deals with molecules moving around. And it makes some assumptions about gases that we have to kind of stick with in order for all of our calculations to work. And the assumptions are true under like 99.9% of circumstances. So the three assumptions are, and I'm going to go through these pretty quickly. I used to have to memorize these for a quiz, but seeing as that's probably not going to happen, you should know them and be aware of them. But I'm not going to ask you them on a test or a quiz, at least not while we're on break or virus-induced quarantine. So the first one, the particles in the gas are small hard spheres with an insignificant volume. So this has two parts. The first part just means small hard spheres means they're tiny, and when they bounce off each other, or when they hit each other, they just bounce off and go their separate way. When they hit a wall, they just bounce off and go their separate way. They don't stick to something. They don't act in any other way weird. And the insignificant volume thing means that they're mostly empty space, which I covered already. When you're talking about a volume of gas, it's really mostly empty space with a few gas particles spread out. The second kinetic molecular theory assumption is that the motion of particles in a gas is rapid. So particles are moving fast. That's one of the things that makes them a gas. It's constant. They never stop. And it's random. So gas particles, they don't have basically attractions or repulsions. They just go in a direction until they hit something, they bounce off, and they go in another direction. That thing could be another gas particle, a wall, you, whatever. The third and final kinetic theory assumption is that all collisions between a gas particle are elastic. So this term elastic, you're going to have to know what it means. But basically, an elastic collision is a collision where when two particles hit, all that energy that they were carrying is transferred from one particle to another, as opposed to being used up in the collision. So a good example of an elastic collision, something you can think of as elastic, and again, this is a physics meaning. This doesn't mean stretchy like, you know, elastic waistband in pants or rubber band. It means that the collision transfers all energy perfectly, none of it is lost. So if you've ever played pool and you hit the cue ball perfectly straight at another one of the balls in play, the cue ball comes to a complete stop, and that other ball leaves with the exact same speed and energy that the cue ball had. It transfers all of its energy from the cue ball to whatever ball in play you hit. That is opposed to like a collision, like a car crash, where if you're at a stoplight, and someone rear ends you, it's not like that car just stops and then you go forward at the exact same speed that car was going when they rear-ended you. No, a lot of the energy is lost to things like friction for your brakes, and also to doing lots of work on the cars. Not productive work like bending and, you know, breaking the car, but work nonetheless from a physics term. So elastic collisions mean all the energy stays. So when gas particles hit each other, they bounce off and they keep all their energy. The energy can transfer to one particle to another, but overall the total kinetic or motion energy stays the same for the gases. So those are the three assumptions of the KMT, kinetic molecular theory, for gases. And then I'm going to go on to one more list, and then I'm going to talk about physical properties. So basically, all gases have these 6 properties, every gas. And they'll be the titles of the next few slides. And again, this PowerPoint will be available, as will the notes I show you in a bit. So all gases have mass. Gases weigh something. They aren't weightless. If you've ever held a full fire extinguisher or a full scuba tank versus an empty one, you can actually, there's enough gas in there that you can feel the difference in weight. Gases have mass. They aren't weightless. It's just such a small amount of mass, it's hard for us to sense it. All gases are compressible because they're mostly empty space. You can compress them closer together. So gases are compressible. Gases will expand to fill their containers. So if you could imagine like a liquid, if I have 1 liter of liquid and I pour it into an empty 2-liter bottle, it fills the bottom half of the bottle because gravity, and that's how liquids work. But if you did the same thing with a gas, and this is kind of weird to think about, but the gas wouldn't stay in the bottom 1 liter of the bottle. It would expand and it would fill out the whole thing. It would move around and bounce off the sides and the top, and it would fill the whole container. So, you know, like when you blow into a balloon, the air doesn't go into one part of the balloon, it fills the whole balloon. So gases expand to fill their containers. Gases diffuse. This is another term you should know the definition of. Basically, diffusion is just movement of one substance through another. You've heard this in biology with active and passive diffusion, where substances are going through cell membranes. But for gases, because they're pretty much empty space, when two gases pass through one another, they don't stop each other. They just kind of go through. This is how we can smell things. So this is how like cologne or perfume works. They're substances that give off gas. They evaporate really quickly to give off gas. And because gases will leave and diffuse until it's spread out through the whole container, whatever that container is, the room you're around or whatever, you can smell that because that perfume or cologne is leaving from the person who's wearing it and going among other places into your nose. Also works with thinking about how farts work. And by the way, when you smell something, that means those particles are actively in your nose. It's a chemical receptor. So if you smell someone's fart, some of their fart particles made it to your nose. So that's happy. I always like to, you know, leave you with some nice, happy tidbits of knowledge. So gases diffuse, gases exert pressure. When we say pressure, we just mean gases hitting the sides of their container. That's what pressure is. So gases are exerting pressure on you right now. In fact, if they weren't, you would die. Human beings are really, really, really poorly evolved or adapted to anything other than standard pressure. So the pressure on you that you don't really feel is actually, I assume, trillions of gas particles hitting you at once. We just don't feel it because we're used to it, and our body doesn't send signals once we get used to something. So gases exert pressure. Pressure is dependent on temperature. And this actually makes sense. Temperature, remember, is just how fast gas particles are moving. So the faster they're moving, the more often they're going to hit the sides of their container, and the harder they're going to hit the sides of their container. So they will exert more pressure the higher the temperature, which is something you know about, and also why you should check the pressure on your tires and add some air or nitrogen in winter usually, or fall, and take some out in spring or summer, because with the same amount of gas, the pressure will be higher when it's warm and lower when it's cold. So even if your tires don't leak, you can still lose pressure in winter, and they can be overpressurized in summer. So this summary slide tells you kind of what I'd like you to know from up till this point. Just 6 properties of gases, the 3 assumptions of the kinetic molecular theory. Again, those used to be really easy points on quizzes where I'd just ask you for those lists, but now since we're only doing online stuff, I'll probably just stick with the math question type quizzes, because, you know, there's no point in questioning you on a list when you can just have that list open in front of you. Okay, so gentlemen, just want to go back and talk a little bit about what we mean when I keep talking about physical properties. So the physical properties we're going to talk about with gases are as follows. Let me move this guy. Pressure, temperature, volume, and later on we're going to talk about number of moles, but for the first few gas laws, number of moles will be assumed to be constant. So pressure, which is abbreviated shockingly P, is measured in several units, which I'll talk about in a bit. But pressure is how hard and how often particles hit the sides of their containers or something else, but generally we measure it based on the sides of their containers. So anything that would increase how hard and how often particles hit the sides of their container will increase pressure. Temperature is measured in kelvins for gas law, always kelvins. If you try to do this math of the gas laws in Celsius, you will be wrong. Remember, it's Celsius plus 273, so if you're given any of these questions, you're given a temperature in Celsius, just convert it to kelvins before you do anything else. Also, it has to go into the math equation in Kelvin. You can't like do the equation in Celsius and then convert the answer. That won't be right. The ratios will be off and the equation will turn out wrong. So always just convert immediately to kelvins if you see a temperature in Celsius for gas laws. Volume is measured in liters or milliliters, and that's just how much space particles take up at a given temperature and pressure. At standard temperature and pressure, we know 1 mole of particles, for instance, takes up 22.4 liters. We're actually going to work through how they figured that out eventually. Number of moles, which is just the number of particles, it's measured in moles, shockingly. And we'll talk about that with the second set of gas laws, not the first 4. So once we get to the 5th gas law. So a little bit about pressure units. There are 3 common pressure units. The metric standard, the SI standard, is a kilopascal. We'll probably use that the most, but all 3 of these can be used. And as long as you use the same one in both parts of an equation, it's okay. You just can't switch from kilopascals to atmospheres like in the middle of an equation. So kilopascals, standard pressure, which is atmospheric pressure, is 101.3 kilopascals. And it's lowercase k, capital P, lowercase a, because Pascal was a guy, so it's named after him. So capital P. I won't kill you on that, but just so you know. Also commonly used in addition to kilopascals are atmospheres, where it just sets like standard atmosphere at sea level. It calls that 1, and we go off of that. So standard pressure in atmospheres is 1 atmosphere, abbreviated ATM. And then millimeters of mercury, which is abbreviated mmHg, Hg being the symbol for mercury, or torr. And I'll talk about that when we talk about how we measure pressure. But the reason we use millimeters of mercury, if you ever look up how a barometer or an open manometer work, they measure pressure, and it's a glass U, and you put mercury or some liquid in it, and you close off one end, and based on the pressure on the other end, the liquid will travel up or down, and it won't be even as it would if the pressure was even on both sides. And they use mercury for that fairly commonly. So millimeters of mercury. Mercury was good because it was heavy, so you didn't have to have a big, tall U. It would change only a little bit for a decent change in pressure. But standard pressure in mercury is 760 millimeters of mercury. It's also called torr. So millimeters of mercury or torr, these are just pressures. And by the way, you can use standard pressure as a conversion factor. So 1 atmosphere equals 101.3 kilopascals, or 1 atmosphere equals 760 millimeters of mercury, or 101.3 kilopascals equals 760 millimeters of mercury. So it's possible to use all of those as a conversion factor to convert between the pressures if you need to. You generally don't need to, but both pressures, if you plug in more than one pressure into an equation, they have to be in the same units or it won't work out. Okay, so the last thing I want to show you, and we'll do more, is this simulation. This is a PhET simulation. I know you guys love those. And we'll do a lab with it, an online lab. But I just want to show you a couple interesting things about the particle. So first of all, it measures pressure. You can change temperature. You can change a lot of things. But I just want to show you, if I put in what are called the heavy particles, notice how they are going, not very fast. Pressure goes up with 50 of them to about 6 atmospheres. If I add 50 light particles, the pressure will double. Twice as many particles doubles the pressure. The reason for that is that even though the light particles are lighter, so, they wouldn't be as strong when they hit the side, you'd think, they go faster. At the same temperature, small particles go faster and big gas particles go slower, to the point where they have the exact same amount of kinetic energy. So when one of those fast-moving light particles hits the side, it has the same impact as one of the slow-moving heavy particles hits the side. So in a gas mixture at least, the particles that are smaller, way less, are moving faster, and the particles that are bigger are moving slower, which is why you don't, for instance, feel like the heavier part of the air, like carbon dioxide at 44 grams per mole, you don't feel that hitting you harder than, say, nitrogen at only 28 grams per mole. They all feel the same because the nitrogen is moving slightly faster than the carbon dioxide at any given temperature. That's one of the reasons gases have these same physical properties when they are, even though they have different chemical properties. So that was just a quick view of this. I will link to this and we'll do a lab with this PhET fairly soon. So you have that to look forward to. Okay, gentlemen, so that's the introduction to gases. You should know kind of those 6 properties of gases and what the kinetic molecular theory of the KMT is and what it says about gases, and why gases are all the same physically, even though they're chemically very different. So you should have some basic idea about that. So what I want you to do is there's a worksheet that is assigned with this, and it deals with the first 2 of what are called the gas laws, which mathematically relate the physical properties of gases. So it's going to be Boyle's law and Charles' law, which deal with the proportions of temperature, pressure, and volume, respectively. Just make sure, remember, temperature has to be in kelvins, so put it into kelvins before you do anything else. Pressure can be in any of those pressure units. Just make sure that if you have 2 pressures, they're in the same unit. So that's all for that. You will turn in the worksheet at a link. You can either print out the worksheet just like with the test and turn in photos of it or scans. You can do it on loose leaf and turn in photos or scans. If you do it on loose leaf, just make sure to clearly label each number problem so I can see what you did. And again, it'll be the same type of thing where you upload it to a Google form. The links are here on the PowerSchool homepage. Also, just so you know, because PowerSchool has been kind of a pain, I'm working on getting a Google Classroom page up. Hopefully it'll be up by the time you see this video. And I will send you an email to invite everyone there. And it should have everything that this PowerSchool page has. I don't know if it can do videos or not, so maybe I'll have to have a YouTube channel too. But we'll see. That is it. I will give you another video or activity tomorrow. And your worksheet is due tomorrow, the 24th, Tuesday at 6:30 p.m. It's a short worksheet, shouldn't take too long. So it is due tomorrow. Okay, enjoy your Monday. Have a good day.